Questions about anything last time? Yeah.
I mean, this is not from last time, but when like a book problem says find a limit or sequence, do we need to just find it or do a proof for it?
Yeah, you should demonstrate how you got your answer. I'm going to say some few words about the, you're thinking of the 1 plus 1 over n to the n problems?
Yeah, I don't remember what problem.
Okay. Yeah, you have to explain your reasoning and how you came to that conclusion. And so I was demonstrating what you did in calculus just to refresh your memory about it. But we haven't done things like the log function or the exponential function or L'Hopital's rule, so you shouldn't use those things. You can use those sort of on your own scratch paper to figure out if you have the right answer. But when you explain your reasoning, you need to use the material from the book, usually from the same section or previous ones. I'm going to say a couple words about some of the homework problems later today. Other questions? Well, this is a famous result, the Bolzano-Weierstrass theorem for sequences. There's another one for sets that we'll talk about later in the course, but it's a very important thing. State and pretty easy to demonstrate also, now that we know some things. So Weierstrass is Karl Weierstrass, is a pretty interesting person. He was studied law and was kind of a lawyer, but he didn't like his job, and he was pretty active in the German pub world. And when he reached the age of 40, he found math and got really into it. And the people like Weierstrass and Dedekind and Cantor were all around at about the same time, and they were very influential in sort of being architects of making analysis a rigorous subject. That crazy-looking beta there is a German S-set. And when you don't have a German S-set to type, it's written in books double S. Well, the big theorem today has to do with subsequences. So I'll define those. So, for example, let's see, minus 1 to the n plus 1 over n. Those bounce up and down. When n is even, that's going to be, let's see, n even. Then that would be minus 1 to the 2n plus 1 over 2n. That would be 1 plus 1 over 2n. So something slightly bigger than 1. And when n is odd, let's see, that would be minus 1 to the 2n plus 1 over 1 plus 1 over 2 to the n, 2n plus 1. That would be minus 1 plus 1 over 2n plus 1. So it kind of feels like this sequence, we should be able to talk about it having two limits, because the, oops. If I were to think about graphing the terms, there'd be, some of them would be piling up at plus 1, and some of them would be piling up at minus 1. So let's see, the first one would be minus 1 plus 1 over 3. So it would be down, let's have here 1, 2, 3, 4, etc. The odd ones would be below here. The even ones would be above. Oops, no, it's -1 plus, so it'd be slightly above. These would be slightly above. 3 would be less above. 4 would be less above, etc. And they alternate up and down. And they obviously get closer and closer, the even ones, to n. When n is big, would be really close above. And when n is odd, they'd be really close below. If n is big. So it feels like this sequence has two limits. And when you want to toss out one of them and keep the other, that's called a subsequence. So if I take, 1 plus 1 over 2n, as n goes from 1 to infinity, and 1 minus 1 plus 1 over 2n plus 1, as n goes from 1 to infinity, are subsequences. And so even though our original sequence doesn't have a limit, these two do have limits, sort of obvious ones. So let's see the formal definition of a subsequence. Let's suppose we have a sequence. Is a sequence. And say we have n1 is less than n2. Let's see, these are positive integers. It's less than n3 is less than ... Then x and k, as k goes from 1 to infinity, is a subsequence. So notice the n's have to get bigger and bigger. That's the key thing here. And notice that k is the new index rather than n. And an easy fact, if xn is a convergent sequence, converges to some value x, and every subsequence of that sequence converges to that same thing. It's kind of an obvious thing. When you take the tail end of the sequence, you know it's in that narrow band close to the limit. And so if you take a subsequence, it's also stuck in that narrow band. So every subsequence of x sub n converges to the same x. So examples, let's say we have xn equals 1 over n. That's 1 over 1, comma, 1 over 2, comma, 1 over 3, comma, etc. And there's lots of subsequences. We just saw that we could take the even ones, 1 over 2, 1 over 4, 1 over 6, etc. The evens is a subsequence. The odds, 1 over 1, 1 over 3, 1 over 5. But even wild and crazy things like the factorials. Let's see, 1 over 1 factorial, 1 over 2 factorial, that's it. 2 factorial is an integer that's bigger. 1 over 3 factorial is an integer that's bigger, and so, etc. In fact, there's lots of ways to choose a subsequence. And of course, they all go to 0. So let's see. How about 1 over 2, 1 over 4, 1 over 8, dot, dot, dot. 1 over 2 to the n's, basically, is a subsequence. Something that's not a subsequence is if the numbers aren't farther out in the sequence. So I can never go backwards and get like after 1 over 8, I couldn't go back and get a 1 over 3. That's not allowed. But because these are subsequence of a convergent sequence, they all converge to 0 without doing any work by the easy fact. So once you see a subsequence of 1 over n, you automatically know it has to converge to 0 without doing any work, now that we know this fact. Questions so far? Here's a fun application of this easy fact. We showed that b to the n goes to 0 as n goes to infinity when b is between 0 and 1. Well, let's see. If b was identically 0, that would be okay. It has to be less than 1. Using Bernoulli's inequality. And being kind of clever about it. Now that we know this fact, there's a much easier way to do it. Let's take let's see, I've got 1 is greater than b is greater than b squared is greater than b cubed, etc. And so that's and they're all bigger than 0, bigger than or equal to 0. So that's a decreasing sequence bounded below. So I'm going to, that's a decreasing sequence bounded below the greatest Loder-Brown property means that the limit exists. So limit exists, and of course it's equal to the inf. And because they're all bigger than or equal to 0, that inf is bigger than or equal to 0. Because that's the greatest lower bound. 0 is a lower bound. And now I'm going to do this sneaky trick to show you what it is. A fun sneaky trick. A subsequence of that sequence would be 1 is greater than b squared is greater than b to the 4th is greater than b to the 6th is greater than dot, dot, dot. That's a subsequence. Okay, let's see. Let's call this limit. Okay, That's a subsequence, and so it converges. So it is a subsequence. So it converges to the same limit. Same. Emphasized. Okay, let's write, I write L equal the limit of b to the n as n goes to infinity. And now I just also know that that same limit is the limit as n goes to infinity of b to the 2n. And of course, that is the limit as n goes to infinity of b to the n squared. And now we use an easy fact that we demonstrated when we were coming up with the basic facts of limits. The limit of a sequence squared is the square of the limit. So this is the aha moment. This is the, now if b to the n converges, so the limit of the squares would be the square of the limit. That's one of the basic facts we came up with in the last couple sections. And that's L squared. Well, not many numbers satisfy L equals L squared. So we get L squared minus L is equal to 0. So L times L minus 1 is equal to 0. The only thing L, the limit could be, is 0 or 1. So the aha, L equals 0 or 1. Why can't it be 1? What? That's it, yeah, well that, but you know, maybe it could sneak its way up and approach 1. It doesn't have to be equal to 1.
It starts below 1.
Exactly, yeah, so that's exactly the point, that it can't be 1. Why can't it be 1? Okay, here's what we had. 1 is greater than b is greater than b squared, etc. And this this b right here shows you that b is an upper bound. So let's see, 1 is greater than b, isn't, and it's the b I'm talking about here. B is an upper bound for all the terms. And so, of course, the limit is strictly is the limit of b to the n is less than or equal to b is less than 1. Okay. So now we've deduced that the limit is 0 without doing much work. Check. Questions about that? That's neat. The book also does an example of c to the 1. Similar reasoning. A c to the 1 over n. Similar argument. builds c to the 1 over n, this is one of the other famous limits, tends to 1 as n goes to infinity. But see, that holds for all c positive. It's to do the demonstration, you do cases. First you do c bigger than 1, then you do c between 0 and 1, and then c equal 1 is a no-brainer. That's the one you don't have to think about. Anyway, it's slightly more involved than the b to the n case. Okay. Well, now I'm going to state the Bolzano-Weierstrass theorem, which is the big subject of the day. Very short and sweet. A bounded sequence has a convergent subsequence. So the important word here is bounded. A bounded sequence has a convergent subsequence. And I think, like the book, I'm going to give 2 demonstrations. My favorite one is the one the book is the second demonstration. So this is the book's proof number 2. All right, so let's suppose we have a bounded sequence. So it's a bounded sequence. That means there's an m, and we can write absolute xn is less than or equal to m for all n. That m is bigger than or equal to 0, of course. Okay, so step 1. Here's the real line. Here's minus m. Here's plus m. And the middle of that is 0. Okay, there's infinitely many xn's. It's x1, x2, x3, x4, etc. So one of those 2 sides must have infinitely many terms. At least one of them. Maybe they both do. So at least one side. Let's see, there's 2 sides. That would be minus m, 0, or 0m. Contains infinitely many xn's. Pick one of them. Maybe there is only one, but pick one. Call it I1. Okay. And now pick an x1 that's in I1. And pick xn1 that's in I1. That's the first term in our subsequence. Okay, now I'm going to cut I1 into 2. I don't know where I1 is, but this is I1 here. So this part is I1. Let's call it A1 to B1. And this would be the midpoint. Call it M. M would be A1 plus B1 over 2. That's the midpoint. And now we're going to cut I1 into 2 halves, like we did above. Cut I1 into 2 halves, like we did above. Let's see, the 2 halves would be A1 M midpoint, comma, and midpoint to B1. At least one of those has infinitely many terms in it, because my I1 has infinitely many terms in it. So pick one of those. Pick one with infinitely many terms. Call it I2. And now here's kind of a sticky point. Well, it's not sticky. I need my subsequence, the numbers, N1, N2, to be getting bigger and bigger. Well, there's infinitely many xn's in I2, so there certainly is one with a bigger index. Since there are infinitely many, xn in I2, there must be one with a bigger index. N2. Okay, N2. Bigger, strictly bigger than N1. Okay, and we just keep doing this. Keep doing it. I can cut it in half again and again. Keep doing this. I get a subsequence. Let's see, it would be xn1, xn2, and I'm making sure my indices are getting bigger, etc. And these are being a nested sequence. xnk is in ik, and the ik's are a nested sequence. I1 is bigger than, contains I2, contains I3, etc. And so our nested interval theorem says that they're closed intervals. The nested, I add the word closed, interval theorem. It says that, remember, it says that the intersection of those i's is not equal to 0. It's not empty. And in fact, since those the size of those things go down to 0, so note the corollary says that if the length of those intervals shrinks down to 0, then the intersection contains exactly 1 point. So the corollary to the nested interval theorem if the bn minus an tends to 0 as n goes to infinity, then that intersection is exactly one point, a singleton. And in our case, the bn minus, let's see, what are the bn's and the an's? Every time I cut it in half. So b1 minus a1, that was the first one, that was m. Then with the next one, I would cut in half. b2 minus a2, I cut it in half, so it'd be m over 2. And then b3 minus a3, I'd cut it in half again. So that would be m over 2 squared. Dot, dot, dot. And you see that bn minus an is equal to m over 2 to the n minus 1. And those certainly go to 0. 2 to the n minus, that's 1 over 2 to the n minus 1 is a subsequence of the of 1 over n's. So we know it goes to 0 without thinking about it. And multiplying by something bounded wouldn't change that. And of course, p is the limit. And that would be the limit of x sub n k as k goes to infinity. That's an easy thing to... So check. That's how one way to do it. Questions about that? That's kind of a famous argument. Have you ever heard this technique for catching a tiger in Colorado? Colorado's kind of a square state. So first you make... oops, what did I do? Sorry. This is a fun thing. Let's catch a tiger. In Colorado. First of all, you have to know there's a tiger in Colorado. And that's the only thing you have to know. Well, Colorado is this kind of a square state. So you make fences, you cut it into 4. The tiger must be in one of those 4 penned-in areas. So you make fences going around Colorado, and then you make those orange fences. Okay, so it's in one of those. So maybe it's in this one. Cut that one into 4 using 4 fences. Using those green fences. The tiger must be in one of those 4 areas. Maybe it's this one. Then you cut that one into 4. And you keep doing that. And eventually, you'll have the tiger in a little cage. Because they get shorter and shorter every time you divide by 2. And so eventually, you're going to get down to a really small cage where the tiger just fits in it. So that's a safe way to catch a tiger. Crazy. But that's a very mathematical argument. And that's kind of what we did in this Bolzano Weierstrass theorem. Oh, by the way, that's a 2D thing, but if you think about those little boxes are interval across interval. And if you look at those intervals, they're nested. So if you know the nested interval thing in the horizontal direction and the nested interval theorem in the vertical direction, you get that the tiger would be the limit of something. It would be in the intersection of all those nested intervals across the intersection. That would be a single point. Here's a fun fact. Every bounded sequence has a monotone subsequence. Got to be bounded. Oh, it doesn't have to be bounded, sorry. Every sequence has a monotone. And remember, monotone can mean either it means either decreasing or increasing. A monotone subsequence. Okay. The book calls these things, I'm going to say, peak points. I'm going to call them vista points. So let's say xn is a sequence. We're going to call xm a vista point. I'll explain why I chose a better word than the books. A vista point if xm is bigger than or equal to xn for all n bigger. So for n bigger than or equal to m. Okay. And the reason I like that definition is that I kind of get a feeling for it. It might be that the xn's bounce all over the place for a while. You know, they might be going like this. But if xm is a vista point, that means it's the biggest one from that point on. So the xn's then would be less than or equal to the next one. Even might come up and be the same as m. But if you wanted to watch the sunset, that's a good place to stand because you look off to the setting sun and nothing's in the way. Okay? So it's a good spot to watch the sunset. And of course the sun is over here. Okay, so that's why I call it a vista point. After this proof, you can forget that definition because you'll never see it again. So there's going to be two cases. The first case is x sub n has infinitely many vista points. Okay, well, let's think about that. Let's pick the first one to be x sub n1. So pick the first one, x sub n1, be the first one in the list. Okay, since there's infinitely many, there's got to be at least one that's bigger than farther out in the series. Since there are infinitely many, B points, there's one farther along with, there's one, I'll call it xn2, with n2 strictly bigger than n1. Okay. Well, the very definition of a vista point, since xn1 is a vista point, xn1 is bigger than or equal to xn2. And now we can keep doing this and keep getting one after the other. Repeat. This is why math is fun. I want you to realize how clever this is. Repeat, and you get a monotone sequence. It's a x1 is bigger than or equal to xn2. You get one that's farther out. It's got to be bigger than this xn2 because it's a vista point, etc. So that's monotone. And in fact, it's what we call decreasing. Okay, that takes care of the case when there's infinitely many. And now the next case is when there's only finitely many. Case 2, only finitely many vista points. Okay, well, once you let's get rid of them. Let's take a point that's past all the vista points. So let's say that x sub n is the biggest vista point. It's the last vista point. Okay. Then let's let n1 be, the very first term in my subsequence be n plus 1. Well, since xn is the last vista point, xn1 is not a vista point. Which means it's not the case that xn1 is greater than or equal to x sub m for all m bigger than or equal to n1. That means there's one out there that's strictly bigger. So there is a n2 bigger than n1 with x sub n2. It's not the case. Yeah, xn is bigger. So there's one that's strictly bigger. Okay, and now we can keep doing this. xn2 is not a vista point. So we can repeat this process and so we repeat, and we get a sequence, let's see, xn1 is less than xn2, is less, in fact, strictly less, etc. And so that's monotone. In fact, this one is monotone. And in fact, it's strictly increasing. So I guess if I wanted to make my theorem sound fancier, I would say every sequence has a decreasing subsequence or a strictly increasing subsequence. But both of those are monotone. And here's how the book proved the back to Bolzano Weierstrass. So here's proof number 1 in the book of the Bolzano Weierstrass theorem. So we have xn as a bounded, it has to be a bounded. This is where I have to have bounded sequence. The fun fact means there's a monotone subsequence. There is monotone, could be decreasing or increasing. Monotone subsequence, x to the n sub k. And so we'd have a minus m is less than or equal to x sub n sub k is less than or equal to a plus m. And if it was an increasing sequence, it's bounded above. If it's a decreasing sequence, it's bounded below. And so, of course, either way it goes, that we have a monotone convergence. So this means it's bounded above, bounded below. And so the monotone convergence theorem says that the subsequence converges. The subsequence converges. Oh, I need to, let's see. I didn't get to talk about lim-inf and lim-sup. Might save that for next time. I wanted to say a couple words about a homework problem. So this is homework 4. Let's see. 3.3, number 12, and 3.4, number 7. These are about related to the fact that 1 plus 1 over n tends to e as n goes to infinity. That's all you need to know to solve these problems. So let's see. This is the definition in the book. And it proved this. This is these are 2 is less than 1 plus 1 over n to the n is less than 3, and they are strictly increasing. So the monotone convergence theorem says it converges to something, and that something is called E. Okay, that was a fair amount of work in the book. But you can answer all those questions knowing only this. And so all of them are fairly routine once you realize what the trick is, except for 12D. 12D is tricky, but I was thinking about taking it off the list. I'm not going to say tricky. It's interesting. I kind of want you to think about it because it's fun to think about it. In fact, you can talk about these problems on Piazza and share ideas. But 12D is so interesting that I've decided I'm not going to grade it. You'll notice the grader only grades 4 problems per assignment. And I carefully choose those to be reasonable and interesting, but not too interesting. So I'm not going to grade number 12D. But think about it. I'm still thinking about what would be the best way to do it.